So naturally, if we can express logarithmic equations in exponential form, then we should be able to go the other way and express exponential ones in logarithmic. So again, paying close attention to this language here, where the base is, where the exponent, and where the answer is, we should be able to write this in logarithmic form. So we have 3 squared equals 9, we know that. So how do we express that as a logarithm? Well, we say it's log, and then the base is right here, so the base is 3, so the 3 goes here. We know that logs are exponents, so the answer is 2, or sorry, the exponential answer, because there's the exponent, is 2, and then the answer part, the 9, goes right there. You can double check. Log 9 base 3 asks, what exponent do I put on 3 to get 9? And we know the answer to that question is 2. Try it again. And if someone wanted to actually put up their hand and try it, they could. Like, oh, I don't know, let's say Tiffany. What's period? What do you think it is? Oh, Tiffany, I'm sorry, that's way wrong. The right answer is log with a base of 2, the answer 16, and the exponent is 4. Log 16 base 2 equals 4. Of course, it doesn't matter what the base is or the exponent. Sometimes we have some neat ones like this one. We know 9 to the power of negative 1. Negative tells us to take the reciprocal, so the answer of that exponent is 1 over 9. How do we write that as log form? Well, there's the log thing again. We put a base of negative 1, or sorry, not a base of negative 1, a base of 9. The answer part is 1/9, and the exponent is negative 1. And the way we say that is log 1/9 base 9 equals negative 1. So going back and forth is going to be a big part of your practice from the textbook, expressing it in logarithmic or exponential forms. Okay, next, we're going to look at some properties of logarithms. So these will pop up as we solve more complicated questions later on. And if we understand some of these properties and rules, then it'll allow us to move forward. So for all of these, we're going to recognize a few things. These properties only apply when your base is greater than 0. So we're not going to have exponents, or sorry, yeah, any exponents that have a base of negative number. Okay, we're only going to be looking at ones when a is greater than 0. Obviously not when a is equal to 0, because 0 to any exponent is 0, and it has its own rules. And we're also, for now, going to ignore the situation where a is 1. Because again, having a base of 1 is a very unique situation, because 1 to the whatever is always 1. So the rules don't necessarily always apply when the base is 1. So what's the first law or property? Well, it has to do when you have an answer of 1. So the base here, a, could be anything, but the answer is 1. Let's think about that. This asks, what exponent do you put on base a to get 1? So it doesn't matter what the base is. There is an exponent that when you put it on base a, you get a 1. And the answer is 0. If you think about it, because if you have any base and you want to get an answer of 1, you have to raise it to the power of 0. So the because here is because a to the 0 equals 1, regardless of what the base is. So it's always this case. in our situation. Of course, if the base was a negative, we might get some other weird ones, or if the base is 0, it gets a little weird. But that's why we're ignoring those cases. But in this case, a to the 0 is always 1, so log 1, regardless of the base, is 0. What's this? So this is log a to the x, base a. So again, we have, what exponent do I put on base a to get this to answer? Well, if we just stop and look at it, it says, what exponent do I put on base a to get a to the power of x? Well, the answer is just x, isn't it? This is sort of like an obvious statement. What exponent do I put on a to get this? Well, obviously it's x because it's right there. The proof for the because is, well, let's translate this to exponential. Base is a, exponent is x, equals the answer of a to the x. So I call this duh, of course. What exponent do I put on a to get a to the x? Well, it's right there. You can almost think of this as like a canceling, an opposite operation, because I have a exponent right here, and I'm asking what exponent do I put on the base a to get this exponent? Well, it's obvious right there. It's almost like the log and the base here cancel out and you're left with just an a. It's not technically what happens, but it's what it feels like. Especially in the next example. So this is an exponential statement. And we have a base a being raised to some logarithm. Well, that logarithm is log x base a. So again, it's similar to opposite operations in this case. The answer is x. May not seem obvious until you write it out as a logarithmic statement. So let's write this out. This here is actually an exponent. Even though it's got a log in it, it's an exponent. Let's write it as a logarithm though. Well, log, what's the base of this exponent? Well, it's right there. So I can put the a there. Okay. What's the answer to this? Well, it's x. So the answer goes right there. And then what's your exponent? Is right here. So log a to the x. It follows the duh principle as well. So it's these last two, number 2 and 3 here, almost like it's opposite operations. When you're taking the log of an exponent, the answer is right in the exponent. This, when you have the logarithm as an exponent, the answer is right up there as well. So it's almost like this part cancels and you're left with x, and this part cancels right here and you're left with an x. Okay? And then of course the first one, anything to the power of 0 is 1, so log anything with a 1, regardless of the base, is 0. So those will pop up throughout the unit, and it's important to just remember them. There's one other little bit of notation we should remind you of or tell you about. Sometimes you'll see just log 27, and there's no base there. So you see there's no base written here. If you don't see a base, it's assumed that you mean log base 10. Okay? This one is called the common log. It's the most frequently used base, base 10. So just like, when we write the square root symbol, we don't write the little 2. When you write the square root symbol, technically there should be a little 2 there, but because the square root is so common, we don't even write it. Same with this. The common log is the most frequently used base. And so we've gotten in the habit of not writing. If you just write log, it's understood to be log base 10. And if you go to your calculator, your logarithm base 10, your common log, is the only one your calculator can calculate. And so they just have a log button. But it means log base 10. All right. So now we're going to try and solve some exponential equations. For these, the strategy will be to switch them all into exponential equations because that's the stuff we're familiar with. So if we're trying to figure out what the x is, we're going to switch to exponential. So for now, these very simple logarithmic equations will be switched to exponential, and then we solve them just like we would have in grade 11. All right. So the first one is asking log x base 2 equals 8. Again, you might be able to stare at it and answer the question, but let's not worry about it. Switch it to an exponential equation. So the base is 2. The exponent is 8. And the answer is x. Now this is a very simple question. 2 to the power of 8 is 256. And that's a much simpler equation to solve. What about b? Log 81 base something equals 2. Well, again, you might be able to look at it and figure out what it is. You know your unknown is the base, your exponent is 2, and the answer is 81. So you might be able to look at it and see that it's 9. But let's convert it to an exponential, then it'll be obvious. So converting this to an exponential, we get the base is x, the exponent is 2, and the answer is 81. Solving this equation, we've seen this before, the square root of 81, and x equals 9. Remember, technically we know it's plus or minus 9, but if you remember for now, we are only doing positive bases. So we can ignore the negative 9 as an answer because that would be a negative base. And for now, we're only going to look at logarithms with positive bases. Let's try another one. So this one says log 9 base x equals 1/2. So again, this starts to get further away from ones that you can just look at and answer. So we're going to go to the process of switching to exponential. Again, our base is x. Our exponent is 1/2. And the answer is 9. So x to the 1/2 equals 9. There's a couple of ways you could write this. You could say, well, x to the 1/2 means the square root of x equals 9. And the opposite operation of square rooting is squaring. Square root of x squared is just x. That's your opposite operation. 9 squared is 81. The other way you could have done this is starting right from this and squaring both sides right away. Here you have x to the 1/2 raised to the power of 2. So those exponents would get multiplied, and you would just get a 1. 1/2 times 2 is 1. And 9 squared is 81. Either way, let's double check see if it makes sense. If I plugged 81 back in here, this would say log 9 base 81 equals 1/2. That means what exponent do I put on 81 to get 9? Well, 81 to the 1/2 is the same as the square root of 81, which is 9. So it works. And one final one. This is log 9 base 1/3 equals x. Again, this is an evaluate one that you could just evaluate. You could look at it and say, what exponent do I put on 1/3 to get 9? But it might not be an obvious answer in your head. It's not in mine. So I'm going to go off and switch it to an exponential. The base is 1/3. The exponent is x. And the answer is 9. Now it looks just like the ones we did in our warm-up, an exponential equation that we solved by getting a common base. I'd like to change it to base 3. So I'm going to change the 1/3 into 3 to the negative 1, raised to the power of x, and change 9 into 3 squared. Multiply these exponents, 3 to the negative x equals 3 squared. Since I have a common base, I can ignore the bases and go straight to the exponents and say, therefore, negative x equals 2, and x equals negative 2. Again, I can stop and think of it for a second. What exponent do I put on 1/3 to get a 9? So that would be 1/3 to the negative 2. Well, the negative part tells me to take the reciprocal, and the reciprocal of 1/3 is 3. 3 squared is 9, so it works. So today is all about just evaluating logarithms, getting used to that. I really want that voice in your head to say, what exponent do I put on a certain base to get an answer? I want you to ask yourself that question as you do this practice. And then when we get into evaluating them or solving them, right now, our best strategy is to take the logarithmic equation and switch it into an exponential equation, because then it'll look like the ones we did in warm-up and in the review yesterday and in grade 11. Eventually, the equations will get more challenging and we'll have to come up with some new strategies, but right now, this is what we're practicing. So, your work comes out of the textbook on page 466, numbers 1 to 4, 6, 9, 10, and 18. And you'll see that number 4D is wrong on the back. The answer is actually 1.40. Good luck.